Good morning, all y'all. Morning, Michael. I have this fear that one day I'm gonna accidentally not stream and I'm just gonna be like talking to myself and being really weirded out that no one's responding. Hasn't happened yet so far, which is good. Good morning, Ryan. There we go. So you guys finished up your midterms now? Those of you who had one on Monday or Tuesday. Finally. Yay! Very exciting! Two next Monday? Oh boy. What classes? DiffyQ and Bio. Whew. Well. So are you guys' finals typically cumulative in this situation where you have exams so close to the final? Benny, come to Friday office hours. We'll have a party. I mean, it's mostly people working on their project and me checking their code, answering the questions. Later. Okay, so kind of like that situation where the material builds on itself. Like, in order to do the last half of the class, you need to have a general understanding of the first half of the class type of thing. That makes sense, especially in, like, math classes. I mean, 16 or 15 weeks is a lot to know, to review for a final. I don't know. But they're almost here. We've almost made it through the semester. The resign deadline's on Friday. Yeah. Question for you guys. What's it like as a student using Respondus Lockdown browser? Thoughts, opinions, complaints? What do you mean by glitchy? Like, how is it? So if you have your test in UB Learns and you have Lockdown browser on, is it just freeze it on? Does it just freeze it on just that web page? Okay, that makes sense. It's just another layer of something to go wrong. That makes sense. Yeah, Benny, I know. So the final exam is pretty much linear algebra stuff. Which means you're writing your work down, and I don't want to tell you this, but there are, like, I mean, you can do it in MATLAB. You can get the answer in MATLAB. And so, like, we want to make sure that you guys are showing your work and doing your work and not having someone else do your work for you. So one of the other instructors mentioned, well, what if we use lockdown? And so I'm trying to get a survey of information so that we can make an informed decision about using it or not using it and how to do our exams. So, Michael, there's a difference between lockdown and browser and monitor. So the respondent's monitor, it might lock you out, but the lockdown browser just, like, do you guys know the difference? Do you have a difference? Okay, Cupcake, yeah, that makes sense. But like the monitor, Michael, is where, like, you can't look away. So anyway, I was just curious. So it sounds like can you open up, like, let's say you have your notes. You can't even see the sun. Really? Okay. So monitors where they're like the computer's watching you, and if your eyes like go in a wrong direction, wrong quote unquote, it'll lock you out. So Squiddy, when you say you can't do anything, so can you open up your notes? Like, can you open up other files on your system that aren't connected to the interwebs? Okay, interesting. That makes sense. It completely, okay, so it like freezes your screen. Got it, awesome. Okay, thank you very much for informing me from a student perspective. We didn't have these issues when I was a student. Okay. If you leave the test closed as well, that sounds awful from my perspective. Okay, that's good to know. Thank you so much. I will take into account this data and report back to the other instructors. Okay, let's go ahead and start class, because it's time to start class. I appreciate your feedback and your constructive feedback. I appreciate the tone everybody talked in and nobody just blurted out and said it's the worst thing ever. Okay, let's start class. So on Monday, we started talking about determinants and calculating the determinant of a matrix that's bigger than a 2x2. We talked about cofactor expansion, where we can use any row or any column, find a bunch of cofactors, and then take the element and multiply by the cofactors and add them all together, and that'll give us our determinant. And it works for any size matrix. So typically we choose the row or column that contains the most zeros, like we did here in this 4x4, where this first column here had the most zeros, so we went with that because then we need to calculate the least number of cofactors. So we're going to finish up our discussion on determinants, and then we will move on into finding the adjoint matrix, and then finish up briefly with Cramer's rule. So the last thing to talk about with respect to determinants is the determinant properties. So there's a whole list of determinant properties, which typically I skip over properties because you can kind of just look them up in the future, or they're not really applicable, they're used more in proofs, but typically I skip over properties, but I want to talk about determinant properties because they can be really useful when we're talking about and calculating determinants. So the first one is the transpose. So if the determinant of A is something, the determinant of the transpose is the same thing. So the determinant of A and its transpose are identical. If we have two rows that are the same, or a row full of zeros, then our determinant is equal to 0. And we can see this, hey look, there's my example from this morning. And we can see this with our alternative method for calculating a 3x3. So let's say we have a row full of zeros. If we do our modified fish method for a 3x3, it would look like this, where this diagonal, and this diagonal, it'd be 0 plus 0 plus 0. Same thing on the other side. This one, this one, this one. 0 plus 0 plus 0. So essentially that row of zeros kind of just eliminates that row to where our determinant is equal to 0. So whenever you see in MATLAB where it tells you your matrix is singular, that's probably an indicator that your matrix has a row of zeros. Singular means that our inverse does not exist, which means that the determinant is equal to 0 because 1 over A is undefined. So if we have a row or column full of zeros, then our determinant is 0, which essentially is the same thing as saying identical rows and columns, because if we have 2 rows or 2 columns, same thing, that are the same, then we can just subtract those 2 rows and we get a row of zeros. So anytime you have all zeros or identical rows, you have a determinant of 0. Another one I'm going to mention, so we've got matrix product and inverse matrix. Those are pretty well defined. Triangle matrix, this is a really nice one that we have, where if we end up with a matrix that's a triangle matrix, where we have a lower triangle of zeros or an upper triangle of zeros, so 1, 2, 3, 0, 1, 2, 0, 0, 1, then it turns out our determinant is just the product of the elements along our diagonal. So in this instance, it would be 1 times 1 times 1, or 1. So that's really nice, really nifty, especially if we're trying to find the determinant of a matrix where it's like an REF matrix, where we have our lower triangle of zeros. So this is a really useful property that we will see sometimes in our homework or in an exam or something along those lines. The last 3 I want to point out are our row operation ones. So what happens when we have row operation 1, row operation 2, and row operation 3? So I'm going to go back to my examples and we'll step through an example. So here I have a matrix, and what I've done is through these row operations I have reduced this matrix into REF. And we're going to explore how our determinant changes with each type of row operation. So there are 3 row operations. We have row operation 1, where we multiply a row by a constant. So multiply a row by a constant. When we do that, our determinant is also multiplied by that constant. So n times determinant of A. When we have row operation 2, row operation 2 is where we swap rows. So row n swapped with row m. And what this does is this changes the sign on our determinant. So it becomes negative determinant. And then row operation 3. Row operation 3, strictly defined, it's our elimination step. Strictly defined, it's where we're going to replace a row by adding that row to some multiple of another row. So I want to stress the importance of the fact that this is a 1 here. We are not multiplying the row by a number. So the row we're replacing, we are not multiplying it. So this needs to be a 1 in order for it to be strict row operation 3. So if we did row 2 equals 3 row 2 plus 4 row 1, this is a combination between row operation 1 and row operation 3, where it's a combination between saying that row 2 equals 3 times, that's not a 3, 3 times row 2, and row 2 equals row 2 plus 4R1. So keep in mind, this here is a combination between 2 row operations, because row operation 3 is strictly defined as replacing the row by adding it to some multiple of another row. We are not multiplying the row itself by a number. And when we do that, when we do strict row operation 3 on a matrix, our determinant doesn't change. So those are my 3 properties of determinants. If I multiply a row by a number, my determinant is also multiplied by that number. If I swap two rows, my determinant changes sign. And if I do a strict row operation 3 elimination step, and my determinant doesn't change. Okay, so let's look at this matrix. This matrix here. Its determinant is -1. And I know that because I'm going to type it in MATLAB. So in MATLAB, if I want to check, I can just type in my matrix. So A equals 4, -3, -3, -3, 5, -3, 3, -4, 1. Determinant of A. My determinant is -1. So going through my notes, what we're going to do is we are going to see how the determinant changes. Going this way. And then I can check to see what my determinant of my REF matrix is. Okay, so if my determinant starts out as -1, and I do this row operation. This row operation is a strict row operation 3, is a strict elimination. Because the number here is 1. I am taking row 3 and I'm just replacing row 3 by adding it to some multiple of row 2. Which means the determinant of this matrix should also be -1. And it is. Because we applied the determinant properties. This row operation, so now in order to get from this matrix to this matrix, I did this row operation. R1 was replaced by 3 times row 1. So this is row operation 1. So if I apply row operation 1, if I multiply a row by a constant, that means my determinant is also multiplied by that constant. So if I multiplied row 1 by 3, I'm going to multiply my determinant by 3. So the determinant of this matrix should be -3. Same idea for the next one. So to get from this matrix to this matrix, I multiplied row 2 by 4. So this is row operation 1 again, which means if I multiplied row 2 by 4, then I'm going to multiply my determinant by 4. So I get -12. Keep going. To go from this matrix to this matrix, I did this row operation. Notice this is a strict elimination, a strict row operation 3, where I just said row 2 is going to be equal to row 2 plus some multiple of row 1. So my determinant shouldn't change. So the determinant of this one should also be -12. To get from this one to this one, I did this row operation. I'm swapping 2 rows. I didn't have to do this, but I did it for the sake of illustration. So to get from this one to this one, I swapped 2 rows. That's row operation 2. If I swap 2 rows, that means my determinant changes sign. So this one becomes -12 to +12. And then to get from this matrix to this matrix, I applied this row operation, which once again, this is a strict elimination step. Row operation 3, because I'm taking row 3 and replacing it by saying row 3 plus some multiple of row 2. So I can have row 2 multiplied by something. That's fine. That's not an issue. Just as long as the row I'm replacing is not multiplied by a constant. So this determinant shouldn't change. So it's also 12. And notice this is a triangle matrix. I have my lower triangle of zeros. So my determinant here is just going to be the diagonal multiplied. So 12 times 1 times 1, which equals 12. Which matches what I found by stepping through my row operations. Which is great. Woohoo! It matches my logical steps. Okay, so we can go this way. We're going to do the same process going this way. So if you're given REF, and you're told which row operations were used, you should be able to work your way back up. So I'm going to erase all of this fun stuff, and we're going to work our way back up. If there was a triangle, if these were zeros as well, yes. My determinant would still be 12 times 1 times 1. It does not matter. As long as you have at least one triangle, you could have both triangles. It's still just the diagonals multiplied by each other. Okay, so looking at this matrix, I know my determinant is 12. Because it's 12 times 1 times 1. Okay, so let's work my way up. To go from this matrix to this matrix, I applied this row operation. Which, like I said before, this is strict row operation 3. So that means the determinant here is going to be the same, which is 12. Okay, keep going back up. To get from this matrix to this matrix, I applied this row operation, which is swapping two rows, or row operation 2. When I swap two rows, that means the sign changes, which means I go from 12 to negative 12. Keep going. In order to go from this matrix to this matrix, I applied this row operation. This is another strict elimination step, or row operation 3, which means my determinant doesn't change. So this is negative 12. Those ones are pretty straightforward. You swap the sign, or you swap rows, you flip the sign. You do a strict elimination step, determinant doesn't change. Here's where it gets a little more complicated. To go from this matrix to this matrix, I applied this row operation. Or essentially, I applied the inverse of this row operation. So go from here to here, I'm effectively saying that R2 equals 1/4 R2. To go this way, I multiplied row 2 by 4. But to go the other way, I need to undo that row operation. Which means, to go from here to here, what I'm going to do is I'm going to divide my determinant by 4. So this becomes negative 3. So for this process going this way, to get from A into REF, I explicitly showed all of my work where I'm trying to get this negative 3 to be a 0. So in order to do that, I multiplied row 1 by 3 and row 2 by 4, just to do it in multiple steps. You do not have to, but I'm just demonstrating all of the steps worked out. Oh, that was not your question. Why don't you multiply it by 4 for R2 equals 4R2? I divide it by 4. Okay, so this 12? Because it's not, row 1 isn't involved in the row operation. So row 1 doesn't change. Okay, so let me talk through this one. So the determinant is 12 times 1 times 1 for the bottom one. It's just the elements along the diagonal. Cupcake Panda, I'm kind of confused on what you're asking. But let's talk through this again. Okay, so I'm right here. So in order to go from this matrix to this matrix, I applied this row operation. I said row 2, or in order to go from this matrix to this matrix, there we go, this way, I said row 2 equals 4 times row 2. I'm working backwards. I'm going from this matrix to this matrix. In order to do that, I need to multiply. I essentially am doing the inverse of this one, where I'm saying row 2 equals 1/4 times row 2. So when we go this way, we are just directly applying the determinant rules because our row operations essentially just follow each matrix as we go along. When we go this way, we need to do the inverse of these rules. So the inverse of this one doesn't matter because it doesn't change. Same thing with here. If you just change the sign, you just change it back. This one, though, if we're going backwards, it's going to effectively be 1 over n times a. So it depends on which way you're going. We're going backwards. So that means if this way, I multiplied it by 4. Going this way, I need to divide it by 4. So my determinant goes from -12 to -3. Same thing again here. If going this way, I multiplied it by 3, that means going the other way, I need to divide it by 3, or -1. And then back to my original one, if I applied strictly row operation 3, my determinant doesn't change, and I can see that my original determinant is -1. Okay, so we can apply these properties in a couple different ways. We can follow them along on your homework or in an exam. You might be given REF and told these are the row operations used in order to find REF. And you can work your way back to find the original determinant. So you might be asked to do that. So you need to understand how we apply all of these determinant properties. So it depends on which way you're going. So if you go down to REF, you apply them directly. If you go up from REF to our matrix, our original matrix, you need to do the inverse. Okay, I do want to point out one caveat to this row operation 1, where if you multiply a row by a constant, let's say we have a matrix like this. And I multiply the entire row. And I multiply the entire matrix by a constant. So the determinant of this is going to be -4. But let's say I multiply the entire matrix by 3. Then I'm going to get 3, 6, 9, 0, 6, 3, 0, 0, -6. So the important thing to remember is for row operation 1, if we are multiplying an entire row, that means for each row that we've applied a number to, or applied a constant multiple to, we're going to multiply the determinant for each row. So this determinant is going to be 3 times 6. -108. You might be thinking, oh, it should be -12, but it's -108 because we've multiplied all 3 rows by that constant. So we've multiplied, wrong one. We've multiplied row 1 by 3. We've multiplied row 2 by 3. We've multiplied row 3 by 3. So for every row we've multiplied, we need to multiply our determinant. So we need to multiply it times 3 for this one. Then multiply that by 3 for this one. Then multiply that by 3 for this one. That's why it's 108 and not just -12. Because the row, every row we multiply the number by, we need to multiply our determinant by that same number. So if I multiply an entire matrix by a constant, I need to multiply my determinant by that constant for every single row in that matrix. Okay, so keep that in mind. That can trip up students. Okay, there we go. That's the last thing to talk about when it comes to determinants. So let's go back to our handy dandy notes and remember why we even care about determinants. What if you did that last step in 2 parts? Sure. You can show multiple steps. That's not a problem. Like this part in 2 steps. This last part. So this last part is yes. So I see what you mean. So if I did R2 equals 11 times R2, I would get, so if I skipped over that, 12, negative 9, negative 9, 0, 11, negative 22, 0, 11, negative 21. So then I would have to go from here to here, which would mean I would get 121, right? That's 11. 132. Wrong one. And then I could say R3 equals R3 plus R2 or minus R2. Then I could get 12, negative 9, 0, 11, negative 22, 0, 0, 1. But notice this matrix is different than this matrix. So this one would be 12 times 11 times 1, or 132. And then you would just work your way back up through one more step. So it doesn't matter which row operations you use. Like I said, I broke out all of my steps. I did not have to. Just keep in mind what the definition of for row operation 1, row operation 2, and row operation 3. Strict row operation 3 means that there's a 1 in front of the row we're replacing. We are not multiplying it by a number, because then we'd have to break it up into 2. Okay, so just keep in mind what are all the different definitions. Michael, glad you're back. Okay, so why do we even care about determinants? Remember that our motivation for figuring out the determinant is to calculate the inverse of a matrix. So here's our formula. A inverse equals 1 over the determinant of A adjoint. 1 over the determinant of A times A adjoint. So we know how to calculate the determinant, and there's multiple ways to do it. We can use cofactor expansion. We can find our fancy fish, or our modified fish version for a 3x3. So that's done. That's good. We're great. Next thing to do, though, is figure out how to do A adjoint, or A adjugate. So to calculate A adjugate, we use this context here. So for any matrix, the adjoint matrix can be calculated as the transpose of the matrix of cofactors. So that means, here's our steps. What we're going to do is we're going to find all the cofactors for all of the elements in all of our matrix. And then we're going to put those into a matrix and transpose it. So let's go ahead and do that. So let's say we have the system of equations. I can write it in the form of ax equals b. This should be secondhand nature to you guys. Writing a system of equations in the form of ax equals b, especially for these smaller ones. You should be able to go back between the two. Back and forth between them. Okay, so given ax equals b, I know my solution is x equals a inverse times b. That's one of the ways we can solve it. There's multiple methods we can use to solve the system now. We can use substitution, we can use elimination, Gauss elimination with back substitution, Gauss-Jordan elimination. We can find the inverse using Gauss-Jordan elimination, which is the long way to do it. It's very long, very tedious, as I'm sure you know. This homework that you're currently working on that's due tomorrow is very long and very tedious and very frustrating sometimes. So we know how to find the inverse using Gauss-Jordan elimination. But the easier way to do it is using this definition. So, A inverse equals 1 over the determinant of A times A adjoint. The determinant of A, I'm going to use my, how much did I do Thursday? No, it's due. Oh, due tonight. Sorry. Weird. Due tonight. Due tonight. Today's Wednesday. Due tonight. Sorry. So I'm going to find the determinant of A. I'm going to do it over here. I'm going to use my modified fish method. 0, negative 2, 4, 1, 1, 5, negative 2, 3, 3. To do that, I just write those same numbers next to it. 0, negative 2, 4, 1, 1, 5, negative 2, 3, 3. And then I look at all of my different diagonals. So this diagonal is going to be 0 times 1 times 3. Sorry, guys. This diagonal is 1 times 3 times 4, or 12, and this diagonal is negative 2 times negative 2 times 5, which is 20. When I add all those numbers up, I get 32. At least I should. Same thing for my other diagonals. So 0, 3, 5, that gives me 0. 1 times negative 2 times 3 gives me negative 6, and then 2 times 1 times 4 gives me 8. Did I miss a sign? This is negative. Negative 8. I add all those numbers up and I get negative 14. Yeah. Okay, so my main diagonals, my non-main diagonals. Subtract those two numbers. 32 minus negative 14 gives me 46. So my determinant of A is 46. So I've done that, check. Now I need to find my adjoint matrix. My adjoint matrix means I'm just gonna find all of my cofactors for every single element in my matrix. And it sounds like a lot, but it's really not that bad. So I'm gonna show my work down here. So start with cofactor 1, 1. Remember to do our cofactors. We are going to take the element. We're going to remove the row and column that it's in. Write our remaining matrix. So 1, 5, 3, 3. And then we are going to apply our grid. For a 3 by 3 or for any matrix, we start our grid in the upper left with a plus. And then I just alternate plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, plus. So for this one, so cofactor 1, 1, there's a plus here. And then I repeat for every single other element. So for this one, take the row and column. So C 1, 2. It's a minus here. So I'm going to do minus, and then my remaining elements, negative 2, 4, 3, 3. For C 1, 3, for this number, remove the row and the column. I have my plus for my grid, and I get my remaining elements, negative 2, 4, 1, and 5. And then I keep going. For C2, 1, I have a minus, and then if I remove row 2 and column 1, I end up with 1, 5, negative 2, 3. C2, 2. I have a plus for my grid. Remove row 2, column 2. I end up with 0, 4, negative 2, 3. C2, 3. I have a minus for my grid. Remove row 2, column 3. I end up with 0, 4, 1, 5. Then my last set. C3, 1. I end up with a plus. And then remove row 3, column 1. I get 1, 1, negative 2, 3. C3, 2. I get a minus. Remove row 3, column 2, and I get 0, negative 2, negative 2, 3. And then C3, 3. I get a plus. Remove row 3, column 3. I get 0, negative 2, 1, 1. It's a lot of writing, but I'm showing all of my steps, all of my work. And then I just have a bunch of 2 by 2 determinants to find. So this one ends up being 3 minus 15, or negative 12. This one ends up being negative 6 minus 12, or negative 18. This minus in front makes it a positive, though. This one ends up being negative 10 minus 4, or negative 14. This one ends up being 3 plus 10, or 13. This minus here makes it a negative. This ends up being 0 plus 8, or 8. This one ends up being 0 minus 4, or negative 4. This minus here, though, makes it a positive. And down here, I get 3 plus 2, or 5. This one ends up being 0 minus 4, or negative 4. This minus, though, makes it a positive. And then my last one is 0 minus, or plus 2, or 2. There we go. I found all of my cofactors. Woohoo! Lots of writing, but smaller numbers to work with. Once you find your cofactors, then you want to put them all in a matrix. I'll call it capital C. So negative 12, negative 8, positive 18, my bad. Negative 14, negative 13, 8, 4, 5, 4, 2. Once you have those all in matrix, you then transpose it. So my adjoint matrix ends up being this matrix transpose, which you can transpose it directly. You don't have to go through this step. It would be positive because it's 0 minus 4, so negative 4, and then negative 4 is positive 4. So to transpose a matrix, you take row 1 and make it column 1. So negative 12, 18, negative 14. Take row 2, make it column 2. Negative 13, 8, 4. Row 3, make it column 3. 5, 4, 2. There we go. There's my adjoint matrix. Woohoo! Party! So much easier. So much easier. So now, A inverse, I've got my determinant. I have my adjoint matrix. So now I just put them together. So A inverse ends up being 1 over 46 times negative 12, negative 13, 5. There you go. You can stop there. You can also multiply through. And you will end up with negative 6 over 23, negative 13 over 23, 5 over 23, 9 over 23, 4 over 23. These are 46. My bad. 2 over 23, negative 7 over 23, 2 over 23, and 1 over 23. Yeah. So you can stop either time. It's fine. Either one works. MATLAB will show you your simplified fractions. So if you want to check your answers in MATLAB, that's what it'll give you if you do format rat. But there we go. I found A inverse. Notice it's a lot simpler. It's a lot faster, in my opinion. It's much faster. And even though there's still a lot of numbers to write, there's less places for errors to concatenate, to kind of cascade. So if you get one number wrong, let's say I got this 4 wrong, then I can just trace my way back. Okay, that means there's something wrong with this 8, which means there's something wrong with this cofactor. So there's just less places for multiple mistakes to kind of snowball. So we found A inverse. Okay, once you know A inverse, then you can solve for x. So x equals A inverse times b. So I'm going to do that. So 1 over 46, negative 12, 18, negative 14, negative 13, 8, 4, 5, 4, 2. And then multiply by b. b comes from my original system, or 6, negative 17, or negative 7, negative 13. And it's just basic matrix multiplication. So 1 over 46, and then I do this row times this. So 6 times negative 12 plus negative 13 times negative 7 plus 5 times negative 13. Same thing for this row, 18 times 6 plus 8 times negative 7 plus 4 times negative 7. And then this row, negative 14 times 6 plus 4 times negative 7 plus 2 times negative 13. When I do that, I get 1 over 46 times, pull out your calculator. Did I type something wrong? Oh, right. Yep. Thank you. Thank you. Yay, I get negative 46. That's a nice, convenient number. Then I have 18 times 6 plus 8 times negative 7 plus 4 times negative 13. Thank you, Benny. And I get 0. That's also a nice number. And negative 14 times 6 plus 4 times negative 7 plus 2 times negative 13. Negative 138. So if I do this, I end up with -1, 0, and -3. So once again, this should be a +3. I don't know why. This happened to me this morning. I thought I would find the error and fix it. But anyway, should be a +3. I don't know where my error was. But here we go. Here's my final answer. So x equals this. Woohoo! So that's another method we can use in order to find a solution. Keep in mind, this is the slower way. So computationally, this method actually is nice. So I shouldn't say computationally, but when you're writing it out, this method is actually pretty nice because we as humans have the opportunity to do these small problems pretty efficiently. When you are thinking about it from a MATLAB's perspective, when you're actually writing an algorithm to do it, we don't typically algorithmically do the solution directly saying A or X equals A inverse times B. Most of the time, when you do left divide in MATLAB, when you're doing things computationally, you're actually using Gauss-Jordan elimination because you can consistently do those row operations every time and get the right answer. It's just easier as a computer to do those row operations. It's harder as a computer to do these determinants because there's so many, like you're repeating the same process over and over again, which sounds great, but it's actually computationally more expensive for a computer to do something like this. So that's why we teach you lots of different methods because there's advantages and disadvantages to each one. Speaking of which, let's do another method. So the last method I want to talk to you guys about is something called Cramer's rule. And Cramer's rule is pretty straightforward. It just requires calculating a bunch of determinants. So here's Cramer's rule. What we're going to do for Cramer's rule is we're just going to find the determinant of A, and then we're going to find the determinant of what's called our AK matrices. So given a system of equations, AK is going to be our A matrix with our B vector inserted in different columns. And then we can use those in order to find our solution, and I'll show you how. But I'm going to copy and paste this system. Copy, paste. And we're going to solve it using Cramer's rule. So like I said, Cramer's rule is just finding a bunch of determinants. So first thing you need to find is the determinant of A. We already know it's 46. We calculated it previously. Then we need to find the determinant of AK, which AK, there's 3 AKs for this system because there's 3 unknowns. So if there are 4 unknowns, there's 4 AKs. If there's 5 unknowns, there's 5 AKs, etc. But A1 is going to be where we take our A matrix, and we are going to replace column 1. Note, A1 replaces column 1 with our B vector. 6, -7. Come on, pen. And -13. And then we find a determinant of this matrix. So I'm going to use cofactor expansion along column 1. So this column. So my grid for that is plus, minus, plus. So my determinant is going to be plus 6 times 1, 5, 3, 3, determinant of that small matrix, minus -7 times the determinant of 1, 5, -2, 3, plus -13 times the determinant of 1, 1, 2, 3. So A1 is just your A matrix with the first column replaced. So A1, replace column 1 with your B vector. Literally just your B values. Okay, when I do this, I get 6 times 3 minus 15, plus 7 times 3 plus 10, plus -13 times 3 plus 2. When I do this, I should get 46. I messed it up this morning. I did it! I did it correctly. Okay, I get negative 46. So that is the determinant of A1. Then I'm going to find the determinant of A2. Determinant of A2, craftily, is going to be my A matrix. But now it's A2, so I'm going to replace column 2 with my B vector. So A1 replaces column 1, A2 replaces column 2. I'm going to do cofactor expansion along row 1. So along this row. So plus, minus, plus is my grid. So plus 0, woohoo! There's a 0. I don't really care what my cofactor is. Minus, I think my pen's battery is dying. Minus 6 times negative 2, 4, 3, 3. Plus negative 2 times negative 2, 4, negative 7, negative 13. So I get negative 6 times negative 6 minus 12 plus negative 2 times 26 minus or plus 28. And I should get 0 for this one. I hope. It worked this morning, but I did it slightly differently. Negative 6 times negative 18 minus 2 times, what's 26 plus 28? 54? Yay! Yep, I get 0. Okay, and then A3. You may have guessed A3 is going to be A. But now I'm going to take column 3 and replace it with B. Oh my goodness, we got ABCs on Monday and now we get the Itsy Bitsy Spider. Okay, so I'm going to use, I'll use column 1 again. So plus, minus, plus. I get plus 0 minus negative 2 times 1, 5, 6, negative 13, plus 4 times 1, 1, 6, negative 7. So I get 2 times negative 13 minus 30, plus 4 times negative 7 minus 6. So when I do that, 2 times negative 43 plus 4 times negative 13. Negative 138. Okay, so I have determinant of A. Determinant of A1 was negative 46. Determinant of A2 was 0. Determinant of A3 was 138, negative 138. Okay, so I find my 4 determinants. Then the last thing I need to do is find my unknowns. In order to find my first unknown, so my first unknown being x, I'm going to take the determinant of A1 over the determinant of A. That's it. So it's going to be negative 46 over 46, or equal to negative 1. So by just finding those 2 determinants, I can easily find my first unknown. My second unknown, same thing. It's going to be y. It's going to be the determinant of A2 over A, determinant of A. So for this instance, it was 0 over 46, or equal to 0. So once again, by adding in another determinant, I can find my unknown. And then my third determinant, z, same thing. Determinant of A3 over determinant of A. In this instance, it was negative 138 over negative 46. Or three. So Cramer's rule looks like this. Find the determinants of my A matrix and all of my AKs. So there's one AK per unknown. And then I divide them. And that gives me my answers. Note the answers I got for this one match more or less the answers I got for this one up here, except for that minus, that this needs to be plus. I can't figure out where I got the sign. Oh, you're right, positive 46. Oh, it does match. Maybe I wrote it down on my paper wrong. Thank you. So the answers I got from Cramer's rule matches the answers I got from x equals a inverse b. Yep, x, y, z, those are just the solutions. They're your unknowns. They're whatever show up in your system, whatever shows up in your x vector. A lot of times they're x, y, z. Sometimes they're the x1, x2, x3. It's just the same order matches over here. So this first one uses A1. The second one uses A2. This third one uses A3. So like I said, there are pros and cons to each of your systems. I have solved the same system using every single method. And for different systems, there's really different pros. I don't know, it just depends. We're gonna learn 2 more methods next week. Which I actually think I like those a lot, just because they're the same thing. You will be asked to use a specific method on the exam. So it will ask you, the way the question is phrased will lead you to a specific method. So it might legitimately just ask you, using Cramer's rule, or using Cramer's method, solve the system of equations. Or find the row echelon form for this matrix, which means you'll have to use Gauss elimination. So the questions on the exam will typically lead you towards a specific method. It might ask you solve the system of equations by finding the inverse of A, and there you might be able to choose which way you want to find the inverse. Do you want to use Gauss-Jordan elimination, or do you want to use your adjoint matrix? So sometimes you might be given one, like you might have to choose between one method or the other, but most of the time you're going to be directed towards a specific method. But yes, I mean, we just learned 2 more methods today. So there's lots of different options. But there we go. That's Cramer's rule. And then we're done. We're done for this week. Yeah, so finish up your homework for tonight. This is by far the longest MATLAB or the longest linear algebra homework you will have. We will do row operations again next week, but it's much simpler, much smaller row operations, and we're only going to work with 3x3 systems next week. So yeah. Okay, with that, final questions? If not, have a great week. I will see you guys next week. So I did not go over specific questions on the homework. I did send out an email on how to do part B of problem 1. I said that in an announcement, so you can go to Ubly Learns and find that announcement. But I did not explicitly do anything in lecture this week that describes how to do parts of your homework. There's stuff on Discord that people are asking about. A lot of times you guys have the same questions and the same person, or not the same person, but a different person posts the same question. So read through some of the Discord. That might help. But it's just, this homework is just long. It's tedious. Check your answers with MATLAB or something every single time. Double check. Because if you mess up on a row operation at the beginning, it's going to mess up everything. So make sure you're double checking your answers every single time you do an operation. Yep. Okay. I'll see you guys next week.